Hi, and welcome to this section of the Calculus 3 Tutor, volume number 2. And in this section of the class, we're going to continue our discussion of Calculus 3, marching our way on through to the end of what most of you guys will cover in your calculus class. We're going to talk about the topic of triple integrals. Let me just pause right here and say that a lot of what I'm covering here and through the remainder of the class is going to assume that you already have been exposed to the material covered in the Calculus 3 Tutor, volume 1. So if you don't already have that, you probably should go ahead and get it, especially with the triple integrals we're doing now, because although I am going to start from the beginning and walk you through it, I'm going to sort of assume that you've been exposed to me introducing the double integrals to you, which is covered on volume 1. That's going to be directly applicable to what we're doing here. Okay, so what we're going to do in this class is we're going to continue on with the triple integrals in this section, and we're going to march through the different types of triple integration and on into the vector fields and stuff that we'll do in here in a little bit. Okay. So what is a triple integral? It's one of those things that you look at for the first time, kind of like a double integral, and you're like, oh my goodness, we did double integrals, that was different, and now we're doing three integrals. Why would you ever do that? Well, we're going to take it one step at a time and tell you why we're doing that, okay? First, let's go ahead and recall the double integral that we did just briefly, which was at the tail end of the volume 1 of the Calculus 3, okay? The double integral, recall, is when you're, just if you can visualize it, you have your x and your y, your x and your y and your z, right? And so that's your coordinate system, and you have a function that sort of hovers, quote unquote. It's a function of x and y, function of two variables, and I use my hand here because I'm sort of indicating that it's a function that's sort of this mountain or valley or something that's kind of hovering over your xy plane. It's kind of hovering there. And there's always a region R that we were talking about when we were doing our double integrals, because the function that I'm talking about is a function of x and y. It's a function of two variables. So when we try to integrate those functions, we have to integrate it over two directions, x and y, because that's what the function is defined in terms of x and y. So you define this region R in the plane. It could be any shape. It could be an ellipse. It could be anything. The way we set the integrals up, we could use any arbitrary shape in the xy plane to integrate this function over. And what we were really doing in that section is we were adding up the contribution of the function as it relates to the region R of the xy plane. Basically, we were integrating the height, so to speak, quote unquote, of that function over the xy plane, over any arbitrary shape that we wanted to choose in there, okay? So if I could summarize it in one sentence, okay, the double integral was integrating a function of two variables, x and y, and we were integrating it in two directions, x and y, because we're integrating a function of two variables over two directions. It makes sense, right? Two variables, two directions, okay? And when we did it in polar coordinates, it was really no different. Instead of a function of x and y, it was a function of r and theta, which is, again, two variables. So when we did our integration over those polar functions of r and theta, we didn't integrate over x and y because that's Cartesian. We integrated over dr and d theta. So it looks different, but it's the same thing. You're integrating over two variables because you have a function of two variables. So to sort of summarize that just really briefly, because it's going to be directly applicable to what we're doing here, just recall for me that the double integral looks something like this, and we sort of, in the beginning anyway, before we actually solved any problems, we said we were integrating over a region R, which is that region in the xy plane down here that I'm actually integrating this function over, okay? We're integrating a function of two variables, x and y, okay? So that's why we have x and y there. And the differentials that we're integrating over are dx and dy. Okay, so this was sort of our general form. You have a function of two variables over x and y. We integrate them over those two directions, basically. And the dx and dy and the limits of integration that we had defined the region R here in the xy plane that we integrated this function over. That's what we were doing, okay? And integration, don't forget, is just a shorthand way of adding up an infinite number of things. So you're adding up the contribution of this function over that region x and y, okay? Now, when we actually boiled it down to where the rubber meets the road, the way we actually broke this down is we had the two integral signs. We had the function of x and y, right? And we had the dy and dx, let's say, because we said before, let me go ahead and change this just to be consistent, dy and dx. You can flip the order of integration, we talked about that, but just to give you sort of an example, what we said was we were going to integrate, and let me go ahead and change colors here just to make it clear. We integrated from, since we're integrating over y, first, y was some function of g1 of x up to some function g2 of x, and we said we're going to integrate from x is equal to a to x is equal to b. So real briefly, I mean, not to really belabor it too much, but if this is x and y, so we're looking down on the xy plane, and our function here that we're integrating is kind of hovering over the xy plane because it's a function of x and y, okay, then what we were really saying here is since we were integrating along y first, we're integrating along this direction first, we had some function here, and we called it g1, and we integrated up to some function here, g2, integrating from g1 to g2 of x. These are just functions of x, okay? And then we integrated from a over to b. And the combination of all this stuff from g1 to g2, which are functions, and from a to b along x, define this region R. That's what we're integrating over. So by choosing g1 and g2, these functions, and our limits of integration, we can sort of define any arbitrary shape in the xy plane that we care about, and we can integrate this function over this region R. Okay, that's what we were doing. So we're going to make a direct extension to what we were doing when we're talking about the triple integrals. That's why I'm giving you a little review here. Okay, so to recap, for double integrals, they're integrating a function of two variables, x and y, and because it's a function of two variables, we're integrating it over x and y in the xy plane. We're integrating over two directions, basically, okay? Now, for the triple integral, what we're going to do is we're going to integrate a function of three variables, x, y, and z, okay? And because there's three variables involved, we have to integrate in three directions. And so it's going to be integrating over dx, dy, and dz. And instead of integrating over an area, a surface area that this function's hovering over, we're actually going to integrate this function over a volume region, dv, okay? So instead of seeing integrals with dA at the end, which is kind of what we had here, well, I guess I erased it, but this could be this dx, dy, and dx, you can sort of replace it with dA. A lot of times you'll see it in your textbook, an area unit, okay? Instead of integrating over some area in the xy plane, what we'll be doing is we'll be integrating this function of three variables over a volume, okay? So in order to get the dimension of volume, you have to have dx, dy, and dz, okay? So burn that in your head. That's really important. And we're going to work some problems here. You're going to see they're not going to be very different from double integrals. I mean, really it's just tedious, but it's the same thing, okay? And we get into the next section where we'll be doing the triple integrals in the cylindrical coordinates. And then even beyond that, the triple integrals in the spherical coordinates. They sound so complicated and so hard, but just please erase your anxiety over it, because what you're going to find is it's exactly the same thing. It's just using a different coordinate system to define the volume that you're integrating over, okay? So what we're going to do now is draw a picture, because I like to draw pictures, and I hope that it makes it clear. So what we're going to do is we're going to draw a little picture of what this triple integral thing is, and then we're going to start working some problems, and you're going to find out that they're really not a big deal, okay? So let's go ahead and start by drawing the thing that we always draw, which is your coordinate axis. And I would encourage you guys to do this yourself for every problem, if you can. I mean, you don't have to, but get used to drawing this because it really does help visualize things. So here's your x, y, and z. It's a three-dimensional system, okay? Now, what we're going to do is I'm going to draw and define for you the following. I'm going to draw several things up here, and I'm going to label a few things, and you're probably going to look and say, what is he talking about? Let me just sort of get it up here and define it for you, okay? What I'm going to do is I'm going to define some arbitrary volume, which is going to be a volume V, or a volume D actually, that we're going to talk about here. So let me go ahead and define, this is sort of like a cylindrical thing, that's why I have the straight sides here. But the tops and the bottom can be sort of any arbitrary shape, okay? You see, that's why I've got lumps here on the top and lumps here on the bottom. This can be very smooth, it could be hills and valleys on the top or whatever, it's some arbitrary thing on the top and some arbitrary thing on the bottom. So what we're doing here is we are defining with the top here connecting down to the bottom, which are arbitrary kind of shapes. This is a volume D. Now, why do they call it volume D? Why don't they call it volume V? Well, most of the books call volume D because if you start talking about V here, then when you get into actual integration where you're talking about dV, it can get a little bit confusing with V and dV. So the volume is D. It's just a letter. Don't let it worry you, okay? So here's a volume D, okay? And this volume D, if you were to shine a flashlight on top and project its shadow, so to speak, down here into the XY plane, it's going to cast a shadow, right? So this shadow, actually, I'm going to draw in a different color. I'm going to draw in this color, and I'm going to do my best to kind of show you that what you have here is, it's maybe not the best representation, but what I'm trying to show you here is that this shadow cast down here, and this shadow is the very familiar region R that we've been talking about from the other sections, okay? So this is the region R. When you look at these books, okay, the region R is always talking about the XY plane, what something looks like in the XY plane. The volume D is actually the entire volume that you're encompassing here, okay? Now what we're going to end up doing is I'm going to have a function here, a function of three-dimensional space. So before, when we were talking about functions of two variables, you had your XY plane, and every point in the XY plane was, you plug in X and Y and you get a third value. You can call it Z, right? And so then you can plot that and it'll sort of hover over the XY plane. Well, a function of three variables, you really can't draw it on a board, because when you think about what you're doing, in this room, for instance, at every point X, Y, and Z, at every single point my finger is at, okay, is a value, okay? And that value could be, let's say I'm measuring the temperature. I'm measuring the temperature here and here and here and here and here and here. So at every point, I have a different value. Now that value is a function of X, Y, and Z, right? Because everywhere I move my finger, I have a different temperature. So I could construct a function of X, Y, and Z that could predict the temperature at different points in space. That would be a function of three variables. Now how do you draw that? How do you actually draw that on a board? I mean, you really can't, because you'd have to have, basically at every point X, Y, and Z, you'd have a different value of temperature. And that's really hard to draw as a surface. So you really can't draw it too well, but you can sort of visualize what's happening. At every single point inside this volume element that we've sort of created here, at every point, there's a different value. And if it helps you to think about it, think about this value as a function, it's like a temperature or something. It could be the pressure at every point in space. It could be the magnetic field strength or something like this. It could be anything that's a function of the space, the three functions of space, okay? So that function that we're talking about here on the board is going to be a function of X, Y, and Z, okay? That function kind of permeates space. At every point X, Y, and Z, whatever my function is defined to be, I calculate a value at that point. And what I'm going to do is I'm going to integrate this function over this volume, okay? So this function is everywhere. It's all dimensions going into the board, coming out of the board, left and right. It's different values. The function calculates a different value at every single point in space. But I don't care about every point in space. I care about adding up the contribution of the function only in this volume element that I've defined here. That's what integration is. And in real life, you might be integrating, later on we'll do a lot more of this. You may be integrating the electric field strength, over a volume. Or you could be integrating you could be integrating any number of things over a volume that would actually mean something, okay? Like you might be integrating the electric field and it might relate to the amount of charge you have inside of that volume, or any number of physical applications, but you're integrating an actual three-dimensional function over 3 dimensions, okay? So in order to pull this off, we have to add a couple of more things to our drawing. Okay, this upper boundary and this lower boundary are arbitrary surfaces, so to speak, because this is sort of a surface on the top and a surface on the bottom, and there can be arbitrary. That's why I've got these squiggly lines here, okay? So the top one, well, actually, let's go to the bottom one first. The bottom one, we're going to say, let me go ahead and erase this and put, this is going to be volume D. Nothing has changed, okay? This bottom surface, we're going to call it Z is equal to some function. I'm going to call it function F1 of X and Y. Let me finish here and let me show you what I'm doing here, so don't worry if this doesn't make sense. The top surface, so to speak, that caps the top end of this can is going to be some other function, F sub 2. That's why there's a 2 there, because it's a different function. It's also a function of X and Y, okay? So what am I saying here? This surface, so to speak, on the top is sort of like my hand. It's cupping it, right? It can have hills and valleys and divots and depressions and mountains and everything else here, and it's going to be a function of 2 variables, a function of X and Y. So at any point X and Y, that's how I'm defining this guy here, because this function of X and Y is going to give me this surface that's going to sit right on the top, okay? And I have a different function of X and Y that defines the bottom surface here. Again, it's kind of cupping it down like this. At any point XY down here, I'm defining this surface here. I plug in X and Y and I calculate a function, a number, I'm going to call it Z, and that is going to be the z value here in this direction that's going to define the actual shape of these boundaries. So here I have everything I need to actually proceed. I've got some function on the bottom of x and y of two variables because it's a surface down here. I've got a different function on the top that governs what the top looks like. It's also a different surface, and they're just connected, you know, by vertical lines here. And I form, by doing this, a volume D. Okay, the volume D. Now, if I take a flashlight and shine down like this, the shadow of this whole thing is going to define a region R here. It's just sort of giving you continuity from the last section before. But what we're going to do is we're going to take a function of three variables, x, y, and z, which exist everywhere. I can plug a value of x, y, and z in and get a number back. That's my function. And I'm going to integrate this function over this volume element D. That is what this entire section is about. Okay? So how do we do it? How do we do it? Well, we're going to work our way up to it slowly, so we're not going to I'm not going to throw you into the grease too much, but conceptually, when you think about it, we need three integral signs. We know that because we're integrating in three directions, okay? And we're going to integrate not over a region R, like we were doing in the section on double integrals, but we're going to integrate over this volume element D, because this volume element D is what we have defined right here. So when we do the integration, however we set up our limits of integration must correspond to this actual volume element. So we're integrating over a volume D, we're integrating a function that we just talked about, x, y, and z, okay? And before getting too technical, we're just going to put dv here. So if you remember back to your double integrals from the last DVD, you know, that we talked about, it was usually written as a double integral over a region R of a function of two variables, dA, which is this dA is area, and it corresponds to the region R. Now dA got busted into dx, or I should say dy and dx, because these two directions give you an area, okay? What you're doing is you see, it's not too complicated. You're just having a function of three variables, and instead of an area, you're integrating over a volume, and you have an extra integral sign here, and so that's just sort of given right like that. Okay, so what we're going to do here is continue on with what we know to be true here, and I'm going to write down a few more things, and we're going to arrive at a very useful thing to actually do our integration. Now let's go ahead and write this a little bit further. Let me say that this is then going to be equal to, let me just write it down and show you. Okay, so don't worry about this here yet, okay? I'm going to put a big parentheses here, and I'm going to put my other integral sign inside. I'm going to integrate from f1 of x and y to f2 of x and y. Integrate. Now I'm just going to integrate my function, x, y, and z. Okay? And then over here, what I'm going to have is dz. Now I'm going to change this parenthetical. I'm going to change colors because I'm going to make it, hopefully, super easy to understand. Okay? And then over here, I'm going to have dA. All right, now let me explain where I'm going here. I'm changing from this form to this form, and I'm slowly unraveling things for you. Eventually, we're going to get down to even a more explicit form here. All right, what am I doing here? This is a triple integral over three directions. Here, the same function. Now, I'm integrating this function. Now, what I'm doing is I'm giving you a little more detail about what this first integral is, okay? What I'm going to end up doing first is integrating along dz, okay? I'm going to integrate along dz. Now look what happens if I actually do this. If I integrate this function along dz, where z is the actual variable I'm integrating over, this thing here, okay, then what I'm going to get in the answer is a function of x and y. Because this is a definite integral, if I integrate this as a function of z, and then I evaluate the limits of integration, which are, they say here, they're functions of x and y, so whatever I get in the end, when I evaluate the limits of integration, this thing returns a function of x and y. This inner thing here, when I integrate this function over dz and then take and evaluate the limits of integration, when you evaluate the limits of integration, you take this function, you plug it into whatever you had for z here after you do the integration, and the same thing with the bottom thing. You're not going to have any z's left over. You're only going to have x's and y's. So once you evaluate this integral, okay, the only thing you're going to have left after you plug in the limits of integration, after you've done the integration, is a function of x and y. So this whole thing is a function of x and y. Now, we already learned how to do double integrals over functions of x and y dA. We did that in the last DVD at the very end. It's called a double integral. You've done that all along. The only thing we're doing here is we're starting with a function of 3 variables, and we're integrating it along the third variable first, dz, and we're going to get our answer, and then we're going to take that and we're going to integrate it over the region R that I conveniently wrote in your drawing down here just for reference. So what we're going to effectively do is we're going to take the region, the function that permeates all of space here in 3 directions, we're going to first integrate it along z. Okay, that's what we're doing first. But in order to integrate it along z, we have to integrate from the lower surface, which is a function of x and y, to the upper surface, which is a function of x and y. That's why the limit of integration are these 2 functions. So we're going to integrate in this direction first, and then after we get the answer, we're going to integrate whatever's left over along x, or I should say along y first, and then along x, and we're going to be integrating it over the region R, because that's the projection of the entire volume element. So all you're really doing, I mean, I'm trying to explain things several different ways to hopefully make it easy, but really all you're doing is you're going to integrate over z first, and then y, and then x, okay? And once you do that first integration along z, you're going to get back a function of x and y, which you already know how to integrate because you've been doing integrals, double integrals, over x and y in the last section on double integrals. So that's all I'm trying to tell you here, okay? So let me go ahead and expand. Now that you know what this is, let me go ahead and write the whole thing in its full glory to show you what you're actually going to be doing, okay? What you're actually going to be doing in your problem. So if R, let me go ahead and switch colors here. If R, the region R in the xy plane, is vertically simple, then we're going to have a certain form, and if it's horizontally simple, we'll have another form. What does vertically simple mean again? I mean, just to refresh your memory, if this is x and this is y, vertically simple just means, and you can go back and look in the section on double integrals, that your region R is defined like this. This is R, okay? And this is the function g sub 2, and this is the function down here, g sub 1, okay? And what it means is it's vertically simple because you can take a little pencil and you can pierce the first function and pierce the second function only one time, okay? Horizontally simple is going to be if your region R is defined by 2 little functions that kind of go vertically like this, and then your regions defined like that. And so going horizontally, you pierce the function one time each, going like this. So basically, the vertically simple regions are what you're going to pretty much run into with most regularity in your classes. I'm just sort of giving you the full spectrum in case you do have a problem like that you can solve. So if this looks foreign to you, go back to your double integrals, and this is all explained in detail here, but this is a vertically simple region. In the xy plane, when the 2 functions that you're bounding by are sort of one on top of another and they're kind of arranged like this, you integrate along y first and then along x. That's vertically simple. Okay, so let's go ahead and write down the form of this triple integral if we're going to do this thing and it's a vertically simple region. What we're going to say is the triple integral, okay, over the volume D, okay, of the function x, y, and z, okay, over the volume dv, which is what we're talking about here. It's a volume element you're integrating over. You have a ton of little volume elements inside here, and you're integrating over every little volume element that you can sort of infinitesimally have infinite number of little volume elements inside of this big volume D. We're integrating over all of them. Okay? What you're going to have here, this is going to be equal to, obviously there's going to be 3 integration signs, so let me go ahead and put the 3 integration signs there. Okay? And it's going to be a function of x, y, and z. Nothing surprising. You're integrating the function. And when there's nothing surprising here, you're integrating along z first, and then along y, and then along x. So you're integrating in the 3 directions. So what are the limits of integration going to be? Well, we just said up here that the first integral we do, the inside integral, is along z. So we're integrating from this surface down here to this surface up here. So we're integrating between these 2 functions here. So I'm going to write these limits of integration in a different thing. So we're going to integrate along f1, which is a function of 2 variables, up to f2, which is a function of 2 variables. These are surfaces, the top surface and the bottom surface, okay? Now whatever we get as a result of that, we're going to integrate along dx and dy, which is down here in the xy plane. We've been doing that all along. So we're going to integrate along y first. So that means we're going to integrate between the function g1 of x up to g2 of x, okay? And then along x, we're going to integrate from the numbers a to b. So if you sort of travel back to this little scribble drawing that I have here, once you integrate along the surface from from F1 up to F2, which is the surfaces here from the top and the bottom of the cylinder, you get that, okay? Then to finish integrating, you got to go along y and along x. So if you're going to integrate along y, whatever this function is along y, then you integrate from the lower function up to the upper function of x. Lower function of x to the upper function of x, and then to finish sweeping the area, you go from a to b. So this would be a and this would be b. That is for a vertically simple region. So that's a lot of talking. I really want you to absorb this because most of the time you're going to have vertically simple regions, okay? Okay, most of the time. So all you're doing is you're taking this function, you're integrating along z, then you plug in these limits of integration. You take that result, then you integrate it along y, and you plug in these limits of integration, which is going to be integrating along y from this function to this function, okay? And then you integrate from a to b, like this, along x. Now, I'll just say real quickly that what you're doing here by having the three limits of integration, dz, dy, and dx, and having all these limits of integration here, what you are doing is, by choosing those, okay, cleverly, you are defining uniquely what this volume really looks like, you see? Because you've defined the surface z from here to here, and then you've defined what it looks like in the y direction, okay, in the y direction by those other two functions there, and then from going from a to b in the x direction, you've done it the other way. So you have x and y and z. Going z this way, then along y, and then along x. Putting all of this together is what actually specifies this volume that you're integrating over. You need all three directions to do that. So this is what you're going to use all the time, almost all the time. I'm going to write down one more thing, only because you'll see it in your calculus textbook, and I want you to sort of know what it means, even if you don't use it very much. Okay, so I'm going to write that down here. If R is horizontally simple, then the integral will be very, very similar, but not quite the same. So if it's going to be done like this, then it will be integral, triple integrals, obviously. Okay, you'll be integrating this function of x, y, and z. Okay, you'll always integrate along dz first. Okay, and the only difference is, if you remember back to your double integrals, when you had the difference between vertically and horizontally simple, the only real difference was you switched the order here. So here you'd be integrating along dx first and along dy. Okay, you flip the order. Now the inner integral is going to be the same exact limit of integration as before. You integrate from that lower surface to the upper surface, so it's going to be f1 of x and y up to f2 of x and y. Okay, that's what this limit of integration corresponding to z is. Then when you integrate along x, this is the only real difference here. You're going to be integrating from h1 of y to h2 of y. Okay, and then here is going to be integrating from the number c to the number d. Now just refresh your memory a little bit here, just so you're not totally lost with this. If it's a horizontally simple region, all that means is that when you're looking down in the xy plane, instead of having your functions like this one on top of another and then from one number to another number, and you have the functions like this, your functions are sort of laying like this. So if you put a horizontal line, they only pierce the function one time, okay? So what you're going to end up doing is, if you can kind of tilt your head to the side and look at it like this, y is the independent variable here and x is the dependent variable. So this function right here is actually h2 of y, and this is h1 of y. Okay, this function's it's a function of y, and this is another function of y. Okay, and then if you were going to complete things here, you integrate from some number here and some number here, and this number is just called c and this number is called d. They're just numbers. So instead of having your functions oriented like this, where they're vertically simple, you kind of tilt your head and you're orienting them like this so they're horizontally simple. So really what all it really amounts to is that if you're doing something where you have a horizontally simple region, you integrate along z first, and then you integrate along dx, and you have to integrate from this function up to this function, which are now functions of y, because you're kind of turning your head over to the side looking at it like this. Y is the independent variable here, so they're functions of y integrating along x. And then to finish it out, you'd integrate along y from c to d, which is what we're doing here from c to d, okay? But I don't want you to lose track of the big picture, because this is a lot of theory, okay? And when you'll see in a minute is when we actually erase all of this and go work some problems, it's not going to be that difficult, because you're going to have a function here. All you're going to do is you're going to integrate along z, plug in your limits of integration, take the result, integrate along y, plug on limits of integration, and then you'll integrate along x and plug in those limits of integration, you'll get the answer. So there's really, not going to be anything more than this going on. It's just that the theory behind it, if you were told to integrate over some specific boundary, then you would have to know how to set it up. You'd have some function here down on the bottom governing this thing. You have a function up here governing what the top looks like, and then you'd obviously have to choose what boundary you were going to actually integrate this thing over in the xy plane as well. And then putting all that together, top, bottom, and then whatever you define in the xy plane, that's going to define what this actual volume D is. And so most of the time you're going to set it up like this, integrating along z from that function f1 to f2, then taking the result, integrating along y, and then integrating along x and plugging in your limits of integration here. So let's go ahead and work some example problems, and I think when we do that, you'll be a lot more comfortable with triple integrals. Okay, so our first problem of the day is going to be a triple integral. Okay, the function is actually going to be y minus x times z. Okay, we're going to integrate along dz first, and then along dy, and then along dx. And the limits of integration are from 2 to 4, -1 to 1, and 0 to 3. Okay, so look at what we have here. We're integrating a function of 3 variables, x and y and z. We're integrating along 3 directions, and then these are just simply the limits of integration along z, the limits of integration along y, the limits of integration along x. So by doing all of this, you're defining what that volume looks like. Okay, what that volume looks like. And because these limits of integration really aren't complicated, you see this looks a whole lot simpler than what we were looking at on the previous screen. Because these limits of integration are just numbers, this volume region that we're actually integrating over is just a cube. It's literally just going from z to z, y to y, x to x, okay? And so you're actually just forming a little cube there. If these were more complicated functions up here, then maybe instead of going from z to z up here, you'd have some weird looking function on the bottom and some weird looking function on the top, and you would define a more complicated looking volume. But when you just have numbers in the limits of integration, you're really just integrating over simpler shapes, simple little constant values, so it's going to form a cube in this case, okay? So, mathematically speaking, what do? What I do when I write this down on my paper is I literally write a curly brace like this, and I work on the inner integral first, and I get the answer, and then I do the next one, and then I do the next one. So that's how we're going to do it here. When you're integrating along z, from here on out, by the way, nothing is different from your double integrals that we've already done in the last volume 1. So if you haven't looked at that, please go look at it now. You've already gotten a lot of practice with what we're going to do here. It's just going to have an extra integral sign. So what we're doing is we're integrating along z, so that means z is what we're integrating over. Anything else, x or y, anything else is just a constant. You must get to the point where you can look at these things and say, okay, I'm integrating along z. X and y are just numbers. They could be, -10 or -54. I treat them exactly as a constant when I'm doing the integration. So what this is going to equal, since y is a constant, the answer to this integral is y times z, okay, minus x over 2z squared. Now make sure you understand that, okay? This is a number. It's like 2, okay? So if I'm integrating over dz and this is like 2, well, this is just a constant. It comes down, and then you have your variable. That's a simple integral from Calculus 1. And if z is a constant, if x is a constant, because it is, here when we're integrating over z, this is a constant, it just comes out. 1/2 z squared. That's just a regular polynomial integral that you've been doing all of your life. You evaluate this from 2 to 4 because those are the limits of integration along z. So you see, it's really not that bad. You just have to know what to hold constant. So when you do this, when you're plugging in your limits of integration, you integrate it along z. So the limits of integration must be plugged in only into the z's, because that's what you integrated over. Everything else is just a constant, okay? So the way this will work out here, actually let me go ahead and write it a little bit down below here. What you're going to have here when you evaluate this definite integral here is you will have y times 4, okay, minus x over 2 times 4 squared. I just plugged 4 into the z squared and 4 into the z, minus, and I'm going to do the same thing with the 2. It's going to be y times 2 minus x over 2, and it's going to be 2 squared. Okay? All I did was take the upper limit, plug into wherever z is, and the lower limit, plug into wherever z is, and I just simplify, and let's see what we get. Okay, so over here, let's not get too crazy. Let's not try to do too many things at once. So let's just rewrite this as 4y, okay, minus 4 times 4 is going to be 16, right? 16 divided by 2 is going to give you 8. So you're going to have 8x here, okay? You're going to have a negative sign here, but I'd rather just go ahead and do it. Let's go ahead and do it this way. Negative 2y, because you have 2y here. Negative times negative gives me a positive here. And then over here, I'm going to have 2 squared is 4. 4 divided by 2 is 2, okay? So you have 2x, and it's positive because of this. Okay, so collecting all of my terms, what I have here is I'm going to have negative 6x, okay, plus 2y. Negative 6x plus 2y. Now notice that when I integrated this inner function here, I integrated this function and I plugged in the limits of integration into the z's, okay, and I got a function of x and y back, okay? Now remember, I took great care to tell you that that would always happen, just to sort of give you a little bit of the theory behind what's going on here. You integrate along z and you plug in to values of z, because that's what you integrated over. You're always going to get a function of x and y back. So when you take this function and you integrate it along dx and dy, this now reduces to a double integral that you've done, you know, in the last section, in the last couple of sections, integrating a function of x and y over x and y. So now you see you've just done another step here, and now it reduces to a problem you've already done before. Okay, so you're actually getting some extra help and practice in doing double integrals as well. Because what we're going to do now, I'm going to switch colors, is I'm going to take this, okay, and I'm now going to integrate. I'm going to integrate it like this. So what I'm going to do is I'm going to, just to make it totally clear to you, I'm going to rewrite everything. 0 to 3, negative 1 to 1. The function is negative 6x plus 2y, and I'm integrating that dy dx. I've just taken the answer, I'm integrating along dy and dx. And I'm going to do exactly the same thing that I did before. I'm going to take, and I'm going to draw a little curly brace, and I'm going to evaluate that inner integral first. Now here I'm integrating along dy, so y is what I'm integrating over. Anything else is constant, including this x. So to actually do this integration, you're going to have negative 6xy, because this is a constant, so it's a number. It comes down, you have your y, because that's how you integrate simple integrals like that. You have a number, then this is just going to be a y come. It's a polynomial integral, okay? Plus, I'm going to have 2 over 2y squared, because this is a 2, it's a constant, 1/2 y squared, that's just a regular old plain Jane integral from Calculus 1. Evaluate this from negative 1 to 1, okay? Evaluate it from negative 1 to 1. So what I'm going to actually have in the end here, plugging in here, I'm going to actually plug in the top limit of integration into the y's and the bottom number into the y's, because I've integrated along y, so when I evaluate the limits I need to plug them into only the y's, okay, because that's what I integrated over. So what I'll have is negative 6x times y, which is 1, okay, plus 2 over 2, I'm just going to say is 1, so I'm not going to worry about it. Plugging in here is going to be 1 squared. I'm going to write it down just for completeness. Okay? Just for completeness. And so I don't run out of space here. I'm going to subtract off. This is plugging in the top. I'm going to subtract off plugging in the bottom. I'm going to have negative 6x times negative 1, because that goes into here. Notice I kept the negative here, negative 6x times this. And then I'm going to have plus, again, 2 over 2 is 1, so I'm not going to worry about it. Plugging in negative 1 here, I'm going to have negative 1 squared. That's going to be squared. So all I need to do is evaluate what that gives me here, okay? So going up here, negative 6x times 1 is negative 6x, okay? Plus 1 squared is plus 1. I have a negative here, so negative times negative is a positive, but then I have another negative 1 here, so this is going to be negative 6x, okay? And then I have a negative distributed in over here. Negative 1 squared is positive 1, but it's times negative, so I'm going to have negative 1 here. Okay, I think you can convince yourself that that's what happened. Now the positive 1 and the negative 1 just add to 0. So all I'm going to have, after all of that is done, is negative 12x. Negative 12x, just adding these two things together. Okay, negative 12x. Now what do? Going back up to the top of the page, you can see that I've done the integral along dz, now I've done the integral along dy, now I need to do the integral along dx. So it's a real simple matter, okay, to take this and finish the integral. So now I'm going to integrate from 0 to 3, okay? The integrand is negative 12x dx, okay? And this is a super simple integral. It's negative 12 over 2x squared, just a regular polynomial integral, evaluated from 0 to 3, okay? So negative 12 over 2 is negative 6, okay? And then on the inside, I'm going to plug in the top value, which is 3 squared minus, and then the bottom value is 0 squared. All I did is I evaluated the outside, I kept it out, and then I just evaluate the limits of integration on the inside. So what you're going to have is negative 6 times 3 times 3 is 9. Okay? And so the answer is going to be negative 54. 9 times 6 gives me 54. And that is the answer. So let's go ahead and recap because I want to make sure, and all of the problems are going to follow this general form. Okay? Integrating over 3 directions, a function of 3 variables, again along 3 directions, dz, dy, and dx. Okay? First we integrated along z, so z is what we integrate over, everything else is constant. We got this as a result. We plugged in the limits of integration into the variable z. We got this, we simplified it down to this expression in x and y. So we've effectively eliminated the z dependence because we integrated along z. We know what the z contribution is. Now we're left with x and y. We take that value and we integrate along x and y using the original limits of integration. Now we integrate along y first. X is now constant, so he behaves like a constant. We get this as an answer and we plug in the limits of integration into the y variables, which we got here. We simplified all this down. We got a very simple answer, negative 12x. We take this and we integrate it along x using the original limits of integration and do everything just as before, integrating a calculus 1 integral. The limits of integration give you negative 54. So what you've done here is you're integrating this function of 3 variables and you've defined a volume by picking the limits of integration like this, okay? And what you're doing is you're really looking at this function and the values of this function along this region, this volume V that we've defined, and we're sort of adding up the contributions at every point in space governed by this volume that we've defined here. So every problem is going to be like this. I mean, this is it. This is the section. All we're going to do now is just some more problems to sort of get you some practice in doing it. But it's exactly the same thing. You integrate along z first, and then y, and then x. And then, you know, that's going to basically be the form of all of these problems. Okay, the next problem is integral from 0 to the natural log of 3. That's actually a limit of integration up here. Integral from 0 to 1, integral from 0 to y, and the actual thing we're integrating is z squared plus 1 times e to the y squared, e to the y squared. And let me just write this down and explain something to you. dx, dz, and dy. Now, notice we've done dz, dx, dz, dy, and up until now we've always done the triple integrals dz, dy, dx. That's what we've done. I told you integrate along z first. Well, that's how everything's derived in the books. That makes the most sense to explain to you, okay, because I can hold my hands and show you the top of the boundary and the bottom of the boundary and show you with my hands what we're doing. That's how the textbooks will derive it. But it turns out that since integration is what's called a linear operator that you'll probably learn about in other classes as you go on and learn about math, it's what's called a linear operator. So because of that, when you have 2 or 3 integrals, you can interchange the order of integration and get the same answer, okay, as long as the function is, quote, well behaved. It's a function without discontinuities. It's a function without crazy singularities that go off to infinity. I mean, as long as it's a well-behaved function, which most of the time it will be, especially in real life, you know, if it's a temperature profile, it's not going to have discontinuities in it, okay? Then you can interchange the order of order of integration. So we are integrating this function dx, that's these limits of integration, dz, that's these limits of integration, dy, and that's this one. And we're going to get an answer. And if you were to take this and then integrate over, you know, z first and then y and then x, or whatever order you want, interchanging the order of the integral limits here, you'll get the same answer every time. And that's just the way integration works. I just want to point that out to you. So don't freak out if you see dx first and then some other ordering here. As long as you're careful to hold the correct things constant, you're going to get the right answer. So working here, okay, we're going to integrate along x. So everything else is constant. The z's are constant and the y's are constant. Notice there's no explicit dependency on x here. That doesn't mean it's not a function of three variables, by the way. It's still a function of x and y and z. It's just that the actual function doesn't change as a function of x. In other words, if you look down the x direction, it doesn't change. There's no hills or valleys, right? So that means there's no dependency in x. That's all it means. So you can still do this integration. It's just that this entire mess here, so to speak, is constant. This entire thing is constant. The z is constant, the 1 is constant, the e is constant, the y squared is constant, because I'm holding everything constant but x. So the answer to this integral is, pretending that this whole thing is a giant big fat constant, is going to be x times z squared plus 1 e to the y squared. All I've done is I've taken this giant constant and I'm putting an x in front of it because it's just a constant. And I'm going to evaluate this from 0 up to y. Now, I'm integrating along x, so when I evaluate my limits of integration, I'm going to plug them into x here. So, doing that, I'm going to have, plugging y into here, I'm going to have y times z squared plus 1 e to the y squared. That's going to be this, minus, okay? And notice I'm going to plug 0 into this x here. So this is just a bunch of other junk, but I'm multiplying it by 0. I'm going to plug 0 here. So I could write all this down, but in the end you're going to get 0 because you're plugging in 0 into here. So the answer, so to speak, for this whole thing is just simply y times z squared plus 1 e to the y squared. That is the answer to this inner integral. And so what I need to do now is take this and integrate that. Effectively what I'm doing is I'm taking it and I'm now integrating it, y times z squared plus 1 e to the y squared. I'm integrating it along the original limits of integration, 0 to 1, 0 to natural log of 3, and I'm doing it dz next and then dy. So all I do is I take the function that I got here and then I continue on with my integration. So now I need to go along z. Okay, now I need to go along z. So what I'm going to do next, this is what I'm going to work on next. I'm going to integrate along z next. So everything else is a constant. This is a constant, this is a constant, and all the stuff in between there. So what I'm going to do to make this a little bit clearer for you to understand and how to integrate it is I'm going to rewrite it a little bit. It's not going to be a big deal, but this is a constant and this is a constant. So what I'm going to do is I'm going to take this and I'm going to distribute it in just like this. Okay, I'm integrating along dz. So what I'm going to have here is y z squared e to the y squared. Just wait for me to finish here and you'll see what it is, plus y e to the y squared along dz. This here is exactly the same as this down here. All I've done is I've distributed in. That's just really all I've done. I've distributed the y into the z squared and the e into this term, giving me this. I've distributed the y to the 1 and the e over here to the 1, giving me this here. The reason is because now it's much easier to see how to integrate it. I'm integrating along z, so I'm integrating along z here, and so y is a constant, y is a constant, y is a constant, y is a constant. So, because they're all just simply constants, what I have is y times e to the y squared over 3 times z cubed. This stuff here is a giant constant, and you have 1/3 z cubed, okay? Plus, and then over here, this is a giant constant here, so really all I've got is z times y e to the y squared. Make sure you understand that. This is a constant, so it just comes down. I stick a z there because this is just like a number, like 2 or 3 or 6, and that's how I integrate this. So this is the solution to the second integral. So what I need to do is take this expression and evaluate it from the limits of integration here, which is 0 and 1. And you'll see it's not too big of a deal to do that. You've integrated along z, so the limits of integration that you have are going to be plugged into the z values here. So what you'll have, starting here with the first bracket, plugging in the top limit of integration, is you'll have ye to the y squared, okay, over 3, and then plugging in a 1, you'll just have 1 cubed. This is going to give you 1, so I'm just going to have, this is times 1, so I'm not going to really write anything down, plus plugging 1 into z here, it's just going to be 1, so you'll have ye to the y squared here. So I've taken 1 and I've plugged it into here and here, and I've got this, and I'm going to subtract off the bottom limit of integration, which is 0. If I plug in 0 here and 0 here, you see the whole entire thing goes to 0. So this is a big fat 0 here, okay? So this thing here, which is ye to the y squared over 3 plus ye to the y squared, that is what I'm actually integrating, okay? But notice that everything is the same on the top, okay? And if I can find a common denominator between this and this, then I can add these two things together. So let me tell you this. What if I multiply this guy right here by 3 over 3? If I take this and multiply by 3 over 3, then I'm going to have a common denominator. I'm going to have a 3 on the denominator of both. So what I'm going to have here when I do this is I'm going to have this term plus 3ye to the y squared. That's going to give me 4ye to the y squared over 3. All I've done is I've found a common denominator here by multiplying by 1, basically, and that allows me to add the top to this top here because they're identical otherwise. Now let's take this and let's integrate it along the final direction, which is going to be integral from 0 to natural log of 3, 4y e to the y squared over 3, and I'm integrating on dy. All I've done is I've integrated along the final direction here that was given by my initial problem, okay? Now, it's very simple because the only variable I have here is y, so I just integrate along y, obviously, okay? So what's this going to be here? Well, this looks a little bit more complicated at first because you have y here and a y squared up here until you realize, what if I use a quick substitution? What if you say that u, this is just regular substitution from calculus 1, is equal to y squared? Then that would mean that du dy is equal to 2y, okay? And that would mean, flipping it around, that dy is equal to 1 over 2y du. I solve for dy because when I do my substitution, I'm going to need to plug it in there. So what the integral actually is going to be is 0 to natural log of 3, okay, 4/3 times y times e to the u, because y squared is now u. But dy is now this stuff, 1/2, or I should say 1 over 2y du. Now you can see exactly why we actually did the substitution, because this y cancels with this y, and now I have a nice cute integral here that I can do. So what I'm going to have is the 1/2 times the 4/3, 4 divided by 2 is going to give me 2, so I'm going to have 2/3 integral 0 to natural log of 3, okay, e to the u du. And I know I can integrate that. You know what the integration of the exponential function is, right? So you'll just have 2/3. Integral of e to the u is e to the u. Limits of integration, 0 to natural log of 3. But you can't actually plug in these limits of integration yet because my integrals in terms of u, my limits are still in terms of y. So I plug in what I know u is equal to. So it's 2/3 e, and u was equal to y squared, way back up here we defined u, that's what it was equal to, 0 to natural log of 3. And now we can actually finally pull it off. So what we will have is 2/3 e, and it's going to look a little bit crazy, e to the natural log of 3 squared, okay, minus 2/3 e to the 0. Because y squared, I'm plugging 0 into here, so 0 squared is 0, so e to the 0, okay? So what we're going to have here is we're going to have 2/3 e to the natural log of 3, and we're going to square it, okay, minus e to the 0 is always 1, so it's going to be 2/3. So this is the answer right here. And it looks like a crazy answer, but that's actually the answer. E to the 2/3 e to the natural log of 3 squared up here in the top minus 2/3. So let's go ahead and recap the problem and see where we landed. This was a pretty complicated looking function. We integrate along x and then z and then y. We integrate this one first along x, holding everything else constant, but there were no x's here, so this is all a giant constant. So we integrated it. This is what we got, and we evaluated the limits of integration given by this. We plugged that in and we got this as an answer. Okay, so then we take that and we integrate along the other two directions, z and y. Integrating along z, we hold y constant. So we did that, and in order to make the integral a little bit more manageable, we did all the distribution in, and we got this plus this, which is sort of makes it a little bit easier to integrate, holding y constant here and here and here. We just actually do these simple polynomial looking integrals. This is just constant, and then you integrate just as if this is a regular polynomial integral. We got this. These are the limits of integration. We plugged in the limits of integration, and when we got down to the end here, we just made a common denominator with this by multiplying by 3/3 that allowed us to calculate this by just adding up the fractions, which is real simple. We take this, we integrate along the final direction, and here is just a simple trick from Calculus 1. And you know, these things don't just come to you in your sleep. You need to play around with them a little bit. You know, you kind of know that if you set u equal to y squared, you're going to take the derivative of it, and it's going to cancel here. So that's what we did. We set u is equal to y squared. When we solved for dy, that put a y down here, which canceled with this one, and we finally got a nice simple integral that we could calculate and then plug in the limits of integration. So that was that problem there, and you can see it's mechanical. The real trick here is just to make sure you're holding the right variables constant. Just like your partial derivatives, you have to hold the right variables constant, and you really have to mentally pretend that they're just a number, and then suddenly when you can do that really well, the problems don't become quite so hard. Integral from -15 up to +13, integral from 1 to e, which is again just a number, and the integral from 0 to 1 over the square root of x. And what we're actually integrating here is z times natural log of x all squared along dz, and then along dx, and then along dy. Okay, so again, we're going along dz and then dx and dy, and so we're going to integrate obviously along z first. So what we're going to do is we're going to look at this integral first, and we're integrating along z, so everything else, which is just this stuff, is just simply a constant. So what you're going to have to solve this integral is natural log of x, all going to be squared, obviously this is just a constant, over 2z squared, 1/2 z squared basically, and you're going to evaluate that from 0 to 1 over the square root of x. So you see this is just simply a constant over 2z squared. So let's go ahead and plug that in. We're going to plug our limits of integration into the z's because that's what we integrated over. Okay, so what we're going to have is natural log of x squared over 2, and on the inside, plugging this into here, the top limit, I'm going to have 1 over square root of x squared, plugging into here, minus 0 squared, which obviously is going to be 0 in the end. Okay, so what I'm going to have here is natural log of x squared over 2 times this guy right here, 1 over square root of x all squared is just going to be 1 over x, because the square root of x squared just gives me the x. So in the end of the day, I'm going to have natural log of x squared over 2x down here. And that's what I have for my first integral, so it's not too bad. Now I want to take this guy and integrate it over x next using these limits of integration here. So to kind of facilitate that, let's go ahead and just rewrite the entire integral, -15 up to 13, integral from 1 to e, and what I'm integrating is natural log of x squared over 2x dx dy. Okay, dx dy. And so what I'm going to do next is I'm going to work on this integration first, so I'm going to integrate along x. There's no y present anywhere, so that makes it really easy. So how do I integrate this guy? You have natural log, something squared, you know, it looks kind of complicated. So my advice to you is, you know, the first thing you do anytime you see a little integral is you want to try to do substitution first, and then if that doesn't work, go into your more advanced techniques that you learn in Calculus 2. So what if you do u is equal to natural log of x? That would mean that du dx is equal to, what's the derivative of a natural log? It's 1 over x, okay? And so that would mean that solving for dx is equal to x times du. Solving for dx, just moving, that's going to be x du. I need that because when I plug it into here, I'm going to need that. Now you can see right away that this x is probably going to end up canceling with this x. Let's just make sure that that's actually what happens. So this is going to be integral 1 up to e. And we said u is equal to natural log, so we're going to have u squared on the top, 2x on the bottom, times dx, but we just found dx was equal to x times du. And you can see right away that in fact that is exactly why we did it, because this x cancels with this x, and now you're actually left with an integral that you can solve. 1 up to e, 1/2 u squared, so it's going to be u squared over 2 du. And this is just a polynomial. You know how to integrate that, right? So what you will have is, okay, what you will have is 1/2 times 1/3 u squared. Constant 1/2 comes out, and then integrating u squared is 1/3 u, I made a mistake here, 1/3 u cubed, okay, 1/3 u cubed. And that's going to be integrated from 1 to e. But you can't actually plug in the limits of integration yet, because this is in terms of u, and your limits are still in terms of x. So you want to go ahead and just plug in what you know u is equal to. So the 1/2 times the 1/3 gives you the 1/6. Plugging in what I know what u is equal to is natural log of x. So I'm going to have natural log of x cubed. And now I can plug in from 1 to e. Okay? And now I know how to do that. So what I'm going to have here is I'm going to have effectively, I'm going to have 1/6. And on the inside, I'm going to have natural log of e cubed minus natural log of 1 cubed. I'm just plugging in the top and the bottom. Now let me ask you this. What's the natural log of e? The way you read this is base e. So e to the power of something gives me e. The only way that can happen is if it's 1. So what this is going to work out to be is 1/6, and on the inside this is going to be 1 cubed. This guy evaluates to 1. E to the power of 1 gives you e. So 1 cubed, okay? Now what's this? What's a natural log of 1? Something to the power, or I should say e, because it's base e. E to the power of something gives me 1. The only thing that can be is 0, as anything to the 0 power is 1. So you're going to have 0 cubed, because it's all cubed. And so obviously 1 cubed is just 1, so what you're going to have over here is 1/6. Okay, what you're going to have is 1/6. So we've done the second integral, we've done it, and we've got a number, which is 1/6. Now let's move over here and finish up the integration. The outside integral is from -15 to 13, 1/6 on the inside, integrating along dy. Okay, and that was just taken from our original problem, the outside limits of integration here. Okay. So to do this is just the simplest integral you can possibly imagine from Calculus 1, 1/6y, -15 up to 13, okay? And then what we're going to have is we're going to have 1/6, evaluating the top limit of integration is going to be 13 minus -15, the bottom limit of integration, okay? And it's going to be 1/6, 13 plus 15. So you're going to have 1/6. What's 13 plus 15? It's going to be 28. Okay, so then you're going to have that the answer is going to be 28 over 6, and you can simplify this simply as 14 over 3, because 2 times 14 gives 28, 2 times 3 gives you 6. So the answer is 14 over 3. So we just took the last thing that we got here, integrated along y, which is a really simple integral, and do it. So let's just recap real quick. The function was given by this. We integrated along z first. This thing was a giant constant, so we held it constant, pulled it out, 1/2 z squared. Evaluate the limits of integration, which we did, and we got this. We integrate this along the other two integrals we have, starting with the inner one, we have to integrate along x. We used a simple substitution, which was given by this, to plug in, and we had a simple integral in u squared that we solved, just from basic techniques in Calculus 1, and plugging in our limits of integration right, we got an answer of 1/6. We took the 1/6 and integrated along the third direction, getting the answer here. And this was, again, a very simple integral to do from Calculus 1. So, okay, the next problem is integration from -1 to 1, 0 to x, x minus y up to x plus y. The function itself is z minus 2x minus y. And we, of course, integrate from dz, and then dy, and then dx. So, it looks more complicated, but it's exactly done the same way. Integrate along z first, then y, and then x. But notice, in contrast to the last problem, the limits of integration are more complicated. They're not just numbers. This is a function of x and y, which is sort of that bottom region, that bottom surface area, so to speak, up to the top one. And then you have some function, you're integrating along y, so you have some functions of x's here, and then these are just numbers in x. So this is a little bit more complicated than the simple cube volume that we were dealing with more. This is a more complicated shape that we're integrating over, is really what I'm trying to say. So let's take it one step. This is going to be a fairly lengthy problem, but only because of the algebra. That's really it. So let's integrate this. We're integrating along z, so everything else is a constant. So what this is going to equal to here is 1/2 z squared. This is a constant, so you're going to have negative 2xz, and this is a constant, so it's negative y times z. So it's exactly as if this was, a number, and this was a number, and that's why they just come down, and you have the variable z that kind of comes out in front of it. And so we've done the integration, so now we have to plug in the limits of integration, x minus y up to x plus y. Now, the limits of integration here is really the only thing that makes this problem lengthy. We're probably going to fill up a fair portion of the board, but it's only algebra. It's not like it's hard to understand math. It's just tedious because you can make mistakes. So since this was an integration along z, we're going to plug this into every place we see a z. We're going to plug this into every place we see a z. And so you can see it's going to get a little bit ugly with the algebra, but we'll work through it. So you have 1/2 x plus y squared. That's the top limit going into here. Let me draw a little bracket here. And you'll have minus 2 times x, plugging this in, you'll have x plus y, minus y times this z is going to be x plus y. So we've plugged this into the top, and we're going to subtract off what we plug into the bottom. So we'll have 1/2 x minus y squared, plugging it into here, minus 2x times x minus y, plugging this into here, minus y times z, which is this, so it's going to be x minus y. Okay, so you can see we have a little bit of algebra to deal with. We've got a bunch of junk squared, and then we've got some more stuff here, and all we really need to do is totally expand it out, collect terms, and hopefully we get something simple, and you'll see that we will get something simple, okay, or simpler, okay? So let's do this. Let's work on this here. You have 1/2. Now you guys should know by now, doing algebra long enough, to expand this. Really all you have to do is x squared plus 2xy plus y squared. It's x squared plus 2 times the first thing times the second thing, and then plus the second thing squared. This is just FOIL. I mean, if you don't know that little trick, you just do FOIL here, and you'll get the answer. So that's what that equals, okay? And I keep forgetting to do this. I want to keep everything totally clear for you. Let me put a little bracket here because we're only working on this first, okay? This is distributing this in. You have negative 2x squared minus 2 times x times y. That's what that is, distributing this into here and this into here. Now let's work on this third thing. Minus y times x, this right here, and then minus y squared, distributing this into here. So we finished that first bracket. Now let's see what the second bracket's equal to. We have 1/2, and we have the same thing here. It's going to be x squared minus 2 times x times y plus y squared. Same thing, it's FOIL. X squared plus 2 times the first times the second, but the second is negative y, so that's why you have a negative sign here, plus the second thing squared, so negative y times negative y gives you y squared. Negative times negative gives you positive. If this doesn't ring a bell to you, it's just FOIL from algebra, so just expand this and you'll get that, okay? Minus, let's go ahead and work on this distribution here. You'll have negative 2x squared right here, and then negative 2 times negative y gives you positive 2y, And working on this third term, you'll have negative y times x here, and then plus y squared. Okay, plus y squared. So we've done the hard part. I mean, we really and truly have done the hard part. And all we need to do now is just, we want to distribute these 1/2s in everywhere, and then we want to collect any other like terms that we can along the way, and we'll find out that we can do some simplification. So I don't want to get too far ahead of myself, so let me just do the 1/2s, taking the 1/2s in here. So you have 1/2 x squared plus 1/2 times 2 is just 1, so that disappears. You'll have x times y, 1/2 y squared. Let me go ahead and keep my little bracket here out to show you what I'm doing. Now we've done this, okay? Now can I add up any of these terms here? I really can't add any x squares to anything here, so I'm not going to worry about it. I'm going to have negative 2x squared. Now I have negative 2xy minus yx, which is the same thing as xy, so this is going to be negative 3xy, just adding this term and this term. And then I'm going to be left with this on the end minus y squared. Okay? Now I'm going to subtract off what I have on the bottom, which is this big long thing here. So I'm going to have 1/2 x squared. Okay? 1/2 times 2 is just 1, so I'm going to have negative x times y. And then I have 1/2 y squared. Okay? And then outside, I can't really add any x squareds to anything, so I'm going to have negative 2x squared. And I have 2y and yx, so I really can't do anything else there. Okay, so what I'm going to have here is I'm going to have plus 2y minus yx plus y squared. And what most of you guys will notice, if you've been paying attention, is there's a little mistake up here, because when I did this here, 2x times x gives me the 2x squared. The 2x times the negative y is going to give me a positive 2 times x times y. So that's that right there. Okay, so that's there. And then that's going to ripple down here, where I'm going to have plus 2 times x times y. Okay, so there's a little mistake up here that kind of propagates its way down. So I encourage you at every step of the way to go back up to your previous step and look at it and make sure that it makes sense to you, okay? So we're almost there. We've got this giant long thing, and then this negative and this giant long thing here. And so we need to continue simplifying this here, and then we'll make our life a little bit easier, okay? So what we're going to do is we're going to work on the top just to continue simplifying terms. So what we have is 1/2 x squared, and we have negative 2x squared. So that's going to be negative 3/2 x squared. Okay? And what I'm going to do is I'm going to put a little dot over this to show that I've actually added those things together. That's just to help me remember what I've done, okay? Now what we have here is xy and then negative 3xy. So what you're going to have here is negative 2xy. Okay, adding these two things together, and I'm going to put little dots over them to remind myself that I've looked at those terms. Okay, and then over here, 1/2 y squared and negative y squared is going to give me a negative 3/2 y squared. Actually, it's not. It's going to give me a negative 1/2 y squared. Okay, negative 1/2 y squared. So you have 1/2 y squared and then negative y squared. So that's going to give you the negative 1/2 y squared there. So that's going to be this. Now we're going to subtract off this big long thing. Let's see what simplification we can do here. Okay, so we have 1/2 x squared and we have negative 2x squared. These two terms right here, this one and this one. So let's go ahead and add those together. And what we're going to have now, the negative sign's on the outside. I'm not even looking at that now. Adding this to this, what you're going to have is negative 3/2 x squared. Okay, now look at what I have here. I have negative xy, I have 2xy, and effectively negative xy here. So I need to add all three of those together, okay? So I have negative xy plus this negative xy gives me negative 2xy, negative 2xy, okay? When I add that to positive 2xy, basically this is going to cancel with all of those, okay? So I'm not going to really have any contribution to that, because negative xy plus this other negative xy gives me negative 2xy. That's going to cancel with the positive 2xy. Okay, now look at what we have left over. We have 1/2 y squared plus y squared. So that's going to be plus 3/2 y squared. Okay? Now before we go any further, I want to just sort of rewrite everything, distribute this negative into everywhere, and then we'll finally collect terms, and I promise you we'll be well on our way to actually finishing this problem. Okay? So just rewriting this stuff, negative 3/2 x squared, negative 2 times x times y, minus 1/2 y squared. All I've done is rewrite this. Distributing this in, you have positive 3/2 x squared, and then you have this negative 3/2 y squared. Okay, so now let's just collect terms and be done with this and move on. Okay, so what we have here is negative 3/2 x squared plus 3/2 x squared, so those cancel, so those drop away and they're not really contributing anything. And then to finally finish the simplification here, you have negative 1/2 y squared minus 3/2 y squared. So what you're going to have is negative 2y squared, and that was us just adding this term here to this term right here. And then finally you'll have negative 2 times x times y here. Okay? So take stock of what we've done and sort of remember what we've started with. We started with this function. We integrated only along z, and we plugged in the limits of integration. The rest of it is just algebra. Okay? The calculus is up here. The rest of it is step by step beating the stuff into shape. Now, one thing I'll say real quickly is, at every step along the way, you know, I didn't do too many things at once. I left the first bracket and the second bracket with the negative sign out here kind of alone. I simplified everything, and then I distributed it in and collected the terms. What I have found in my experience is if I do too many things at once, like if I tried to distribute this negative in up here and add the terms together, I'll probably make a sign error. So I've sort of, it takes more paper, but you keep everything separate and then combine it at the end, and that helps. So we've integrated and we've got a function of x and y. Now we need to take this and integrate along dy and dz. So we're going to do that over here. So let me go ahead and switch colors because we're done with the first integral. And effectively what we're doing, just rewriting things here, is we're integrating from negative 1 to 1, up from 0 to x, and the answer that we got down there was negative 2y squared minus 2xy, and we're integrating dy dx. Okay, dy dx. So we've taken what we've done before, and all we're doing is we're integrating it over the other two directions here. Okay, so it's real simple. The first thing we're going to do is we're going to work on the inner integral, and I promise you it's not going to be nearly as ugly as that first one. Let's integrate over y first. So y is what we're integrating over, and x is constant. Okay, so what we're going to have here is negative 2 over 3y cubed, because this is just a constant there, okay, minus 2x over 2y squared. Okay, so this is a constant, so it comes out 1/2 y squared, just a regular polynomial integral. This is a constant, 1/3 y cubed, and we're going to evaluate this from 0 to x. Okay, so let's do that. What we're going to have here is negative 2/3, and then plugging x into y here, because we're integrated along y, so every limit of integration must be plugged into y. What we're going to have is x cubed minus 2 over 2 is simply 1, so we'll have x times x squared, plugging x into here, okay? And that's the first thing. Subtracting off the last thing, what you're going to find is you're plugging 0 into here, and you're plugging 0 into here, so everything is just going to give you a big fat 0. You're plugging it into here, and you're plugging it into here. It's not going to contribute anything. You're just going to get 0. So you see how things are simplifying. Negative 2/3 x cubed minus x cubed. Okay, that's what we're doing here. And so we want to, we want to simplify this, so we're going to rewrite it as negative 2/3 x cubed, and what I'm going to rewrite this as is negative 3 over 3x cubed. You see, 3 over 3 is 1, so I really haven't changed anything. It's just that I'm trying to get a common denominator here so I can add these two things together. Okay, so it's negative 5/3 x cubed, because 2 plus 3 is 5, so negative 5/3 x cubed. So that's the answer. So you see, there's a huge amount of steps for the first integral. Second amount of steps, second integral is not too many at all, negative 5/3. Okay, so let's go ahead and take this integral, okay, and integrate along the outside, which is negative 1 to 1, negative 5/3 x cubed dx. Okay, and that's simply going to be negative 5/3 okay? And then it's going to be times, and then you're going to have 1/4 x to the 4th power, just a regular polynomial integral from calculus 1 from up to -1 to 1, okay? So to multiply these fractions, you'll have, this is going to be -5/12 x to the 4th power from -1 to 1, okay? And so what I'm going to actually have here is I'm going to have -5/12, okay? 1 to the 4th power minus -1 to the 4th power. Okay? So what I've done is I've taken this top thing and I've plugged it in, I've taken this bottom thing and I've plugged it in. And so what you're going to have is -5/12, and on the inside you're going to have 1 to the 4th is 1, -1 to the 4th is also +1, so 1 minus 1. So you'll have -1 minus 1, I'm sorry, 1 minus 1, which is going to give you 0. So it's going to be -5/12 times 0. And after all that incredible amount of work, the answer that the entire integral is going to be 0. And by the way, you know, it's kind of a little sick joke in life, I think, that the more complicated problems in calculus that you get to, that you know you've been doing in calculus 2 and now in calculus 3, a lot of times you'll do a page or 2 or 3 of work and you'll get 0 at the end. And let me give you one piece of advice. It's very important for those integrals that you actually get 0 as an answer to actually go in and double check them and triple check them and quadruple check them. The reason is because if you check your answer in the back of a book somewhere and the answer to the integral is 10 or 20 or 29 or something, then you'll pretty much have a pretty good idea if you've done the math and you get this exactly the same answer that you've done the right thing. But if the book has an answer of 0 and you also calculate an answer of 0, there's a lot of different ways where you could have screwed up your math somewhere but still happen to get a value of 0. In fact, I'll confess to you, the first time I worked my own problem, okay, and then I know, you know, I worked it and I got an answer of 0, and I knew that that's what the answer should be, so I was, you know, very happy, and that was it. Well, going through and checking my math, I realized that I actually had an error way over here somewhere in this math here, and it carried down and it carried down and propagated through, and in the end I still got the answer of 0, but the actual math was wrong. So when you get an answer of 0, then I suggest highly that you double and triple check your work. So coming back, we integrated this value here. We held x and y constant. We got this, plugged in the limits of integration, and here's what we got. Now, we had to expand all this stuff and do it very carefully to keep all of our signs right, and we finally got an answer of -2y squared minus 2xy. We took that and we integrated along dy and dx. Working with the first integral first, we held x constant, calculated this, plugged in the limits of integration, got a very simple answer here, -5/3 x cubed. We took that answer, integrated along x. It's just a regular integral from calculus 1 at this point, and you know how to do that, and you get an answer of 0, okay? So that is you know, probably one of the more complicated triple integrals you can get, but you can see the process is pretty bulletproof. You integrate along one variable, and then along the next, and then along the next, holding the appropriate variables constant in the process. We have covered a tremendous amount of very, very important material in this section, okay? Triple integrals. It's the kind of thing that you flip to in the book. It looks incredibly hard and intimidating when you see not 1, not 2, but 3 integral signs, and you have 3 different crazy looking limits of integration, but really you just start at the inside, integrate, and hold all the other variables constant other than the one you're integrating over, okay? And then once you do that, you get the answer. You plug it into the next integral out, okay? You integrate, again, holding the proper variables constant, and then do the thing a third time. So what you're doing when you do that is you're taking it and you're integrating along the 3 directions. And so you've defined this volume element that you're integrating this function over, and you're really just summing up the contribution that the function gives along every point in space inside that volume. And so the volume can be quite complex, and like that second problem that we did, can lead to quite a bit of algebra. If the volume is actually kind of complicated looking, it can get ugly, but conceptually, it's not that hard. You're integrating along 3 directions, okay? And so let me give you one little prelude. When we go into the next section after this, which is triple integrals in cylindrical coordinates, and then the following after that, triple integrals in spherical coordinates, don't let those words scare you, okay? Because we're doing exactly the same thing. We're going to integrate along 3 directions, and the idea is the same. We define a volume element. We're going to integrate some function of 3 variables over it. The only difference is instead of x, y, and z Okay, we're going to integrate along some different coordinate systems that are better suited to certain kinds of problems. Just like the polar double integrals that we did before, the double integrals were better suited to problems with circular symmetry, and it was really simple to do those in some cases, and that made it easier for us. We move into the cylindrical coordinates and the spherical coordinates. The problems in those cases, when we use those coordinates, are going to be yet simpler still to do. And so you run into those all the time in real life, and we'll get there. So here was a good introduction to triple integrals. We're going to go on and do the next couple of sections and keep banging away at it in different coordinate systems. With practice, holding the right variables constant, checking your work line to line. I know it's tedious, but you have to do it. You'll get the answer, and you'll get a lot of good practice and get comfortable doing these types of integrals.